Okay, good morning, guys. We're going to get started here in just a few seconds. I'm going to crack the window here now. It's getting a little warm. Oh. So I got a few emails from folks who told me that they want to student teach this section or that section, and I wanted to address one or two little things there before we do that. I'd like to just first make sure that everybody who is involved in that discussion is here. Give me 1 minute. Finding my email exactly what I've got so far. So there was a little bit of confusion, and I think two people happened to request the same section. So let's see. This email. Where is this? So Haley and Tahara. Okay. I think we can sort this out without any sort of real troubles. But I just want to make sure. So are Haley and Tahara both here?
Yes, I'm here.
Okay, Tahara and Haley. So Tahara, I think you sent me that you were interested in student teaching section 3.1 on the power rule, right?
Yes, that's correct.
Okay, and Haley, I think you sent me at first that you wanted to teach 3.1, but mentioned the product rule. So I think, and then later in an email you clarified that you wanted to do 3.1 on the power rule. So that means that you guys both requested the same section, although there was a little bit of confusion.
Professor Fieldsticker, I requested the power rule and quotient rule also, and you sent me an email back saying that I could do it. I think, I'm not sure who requested it first, but you responded in an email saying that I could do it, and we were going to meet on 120.
Yeah, so this is a first come, first serve type thing. And what I've been doing is as I get these emails, I'm adding them to a spreadsheet. And what we're going to need to do is we're either going to have to pair up on some of those, or we're going to have to split and do slightly different things. So let me see what I have saved in my spreadsheet here. Give me just 1 second for Excel to load. So was that Thomas Breen just talking there?
Yes, sir.
So I have you down for the product and quotient rule, section 3.2, and you were the first person to email me, so I gave that to you. Is that not what you had intended?
Oh, I'm sorry, I misheard. Yeah, that's what I intended. Never mind.
Okay, cool. And then Hannah sent me an email also during class the other day requesting 4.4 on L'Hôpital's rule, and nobody else asked for that, so that's the one I go ahead and wrote down for Hannah. But then we need to sort out the conflict in the request between Tahara and Haley. Now you guys both emailed me right around the same time. It was all during class, but Haley's email came in at 11:41. Her first email came in at 11:41, and Tahara's first email came in at 2:57. So strictly speaking, Haley has the dibs on 3.1, which is the power rule. Um, Haley, are you still wanting to teach 3.1 on the power rule and the exponential functions?
Well, I would like to, but I wouldn't mind teaching something else. I just remember that the most from high school so far.
I understand. Yeah, that tends to be one of the more memorable things. So then Tahara mentioned that I think she would be willing to co-teach 3.1 with you, or if one of you is willing to do 3.2 instead, then we can split it like that. So what would you guys prefer to do? Would you guys rather work together on 3.1, or would you rather one of you take 3.1, which is on the power rule, and another take 3.2 on the product and quotient rules? Neither of them are especially hard.
Well, I don't really mind either way.
Okay, and Tahara, I think you mentioned that you would be okay co-teaching 3.1. How would you feel about doing 3.2 on the product and quotient rules instead? Any strong feelings there one way or another?
Yeah, that's okay too. I can do that.
All right then, so I want to get this sorted out for sure now. If I'm going on the first come, first serve thing, technically Haley did get her email in first, so she would have dibs on 3.1. And then Tahara, would you rather co-teach 3.1 or do 3.2 on your own?
I can work with her if she doesn't mind.
How do you feel about that, Haley? Would you like to work with Tahara together on 3.1? I think we may have more students than we have sections, so having a couple people pair up would be nice.
Yeah, that's fine with me.
Okay, so I'm going to put you guys down to co-teach section 3.1, which is the power rule and exponentials. So maybe one person could do the power rule and another person could do the derivatives of exponential functions, or you could work together. I'd like you guys to exchange contact information, so go ahead and pop open the chat and send each other PMs with whatever mechanisms of contact you like, phone numbers or emails or whatever that is. I'll go ahead and put you both down for that section as a co-teach. And then just make sure that you split the duties equally, right? We need to go back and forth and make sure everybody's getting a chance to talk and everybody feels like they did a fair amount of work. So where are we here? Haley Rockmiller, we're going to put you in for 3.1, power and exponential. And I'll do the same thing for Tahara. 3.1, power and exponential. So you guys are going to co-teach that, and the date that we're going to cover that is, let me pull up the syllabus. That's going to be the first day of week 4, which is the 25th of January. So the lecture day there is 125. And I'm going to put that in, which means that we'll need to have our meeting about your lecture materials, our first meeting a week before then, which is 118. So after I get this all typed in here, I will share my screen with you so you can see everything and record this for your own purposes. It's very important to stay organized on this stuff so that everything flows nicely. Alrighty. So we've got Thomas doing 3.2, Hannah doing 4.4, Haley and Tahara working together on 3.1. You can divvy up the responsibilities there however you like. Again, my recommendation is that you do several short YouTube videos, 5 to 10 minutes in length. And you can separate the material however you want, but make sure that you read and take notes and have some idea of how you want to do your thing by January 18th, because that's when we're going to meet for a little discussion of your materials and a little rehearsal. Now, while I'm here, let me go ahead and share this. I haven't cleared my inbox for today, so it's possible if you've emailed me since then that I don't have this in here, and I'd just like to square away as much as we can right now. Okay. So Katie, I've got Katie interested in section 4.9, which is that antiderivatives? What's my memory? 4.9, yeah, antiderivatives. Okay, I'll go ahead and put you down for that, Katie. Oh, sorry, that just finished. Katie. So we're going to do 4.9, which is antiderivatives. And we're expecting to cover that section. Where is it? Applied optimizations, areas, sums, definite integrals. We reach back to talk about antiderivatives. Oh, where did that go? That's going to be, it's actually a part of this discussion here after spring break. Yeah, so I think normally I do that when we cover 5.3. So this would be, yeah, it's actually not in the syllabus explicitly. That's my fault. But it would be in around the same time we do this. So we'll attack 5.1, 5.2. Let's say that we talk about antiderivatives. We can do it either before we introduce the Riemann sums or when we come in here to talk about indefinite integrals. Let's say we do it here, 315, before we talk about areas and sums. That will kind of prime us nicely for that. So we're going to say the lecture day for that is 315, March 15th, to the first day back from spring break. All right, Katie? Not the rehearsal, that's the lecture day. And that would mean that our rehearsal meeting would kind of de facto be scheduled for a day during spring break. Is that okay with you, Katie? Are you okay meeting for that rehearsal on the Monday of spring break? If not, we'd have to do it earlier.
I think that'll be okay, but I'm not completely sure.
All right, I'm going to put it in tentatively now for the Monday before spring break. If we need to do it on a different day because you're going to be out of town or whatever, just let me know. And we can move that back to any time in the first week of March. But it needs to be at least a week before the day of the lecture, so you've got plenty of time to take my feedback and use it. So I'm going to put it in right now for 3/8. And then if you're going to be out of town, make sure you let me know before the start of March. All right?
Okay.
Okay, does anybody else want to lay claim to any sections, or has anybody else emailed me and not gotten a response back yet? It's okay if you haven't decided. We do still have, you're allowed to wait until the end of next week. So no big rush, but a lot of these sections are early on. So we want to do this quick and start working on it now, because most of the easier sections to student teach are towards the beginning of the class. Oh yes, yeah, of course. I'm sorry, I just copy pasted this out of the roster, so this is as it is there. I'm sorry. Still deciding. Okay, so I will tab that away. We can get back to the official class material. I'll go ahead and make that change. And I don't think there's any other bookkeepy stuff, so we can go ahead and start talking about mathematics. All right. And let me just remind myself, we wanted to, talk a little bit about limits today. We're going to do the intuitive approach to limits today. So let's do it. All right. So this is MAC2311, section OH1. Today is a lecture, and the date is 1/8/21. Today we're going to talk about limits of functions. Which is section 2.2. 2.1 doesn't have a lot of good homework problems. It's all kind of numerical stuff, and you plug and chug in the calculator, and I found that it doesn't help people build intuition. But the 2.1 material isn't completely worthless. So I want to show you something neat in Desmos that I wanted to show you guys last time, but I couldn't find my Desmos login. So I've since found that. We'll come back to this. But where is my tangent line thing here? Is this it? Yeah, okay. So what we are hoping to get at, remember from my little intro last time where we talked about the two major problems in calculus, the area problem and the tangent line problem. Our goal in the first part of this class is to find the equation of these purple lines. So you see here, I've got this point labeled as the point of tangency. And then there's this purple line, which is called the tangent line to this red graph. And remember, we talked about the graph being a ski slope or a hill or something, and the purple line kind of being like the guy skis, or the direction they're pointing as he skis along the slope. So you can kind of see what a tangent line looks like as I move the point of tangency around here. Notice that when the function is decreasing, like it is everywhere over here, the tangent line points down. And when the function is increasing, like it is over here, the tangent line points up. And the trick to getting a tangent line, let me fix this at a certain point, is, let's see now, how can I do this? Oh, there's no nice way for me to draw this in here, is there? Is to look at a limit of what's called a secant line. So I'll see if I can draw in a secant line here really quickly for you. So what would we have? That point would be 6, 4. So, and if I wanted to do it from there to there, I'll draw the pictures by hand. It'll be easier and take less time. So the point of a tangent line, you know what, let me save all of that until we get to the section on tangents. It'll just be better. We'll start with limits today, and I'll put together another Desmos thing so we can talk about that after we have limits. Limits are the foundation for all of this stuff. Basically, these tangent line things, they show up as limits. And the same is true for area things. They show up as limits. So in order to get into any of that, we need to talk about what limits are. Limits are intimately connected to the idea of open intervals that we talked about last time, in the sense that we're interested in what happens not at a point, but as you sneak up on a point. So let me remind you a little bit about graphs of functions. I'm sure everybody remembers this. If I have a function and I draw the graph y equals f of x, then any point on that function or on that graph is of the form a comma f of a. All right, so this y value over here is f of a. And the main thing I want you to get from this picture, which is very simple, is just that this thing is always f of this thing. So if I came over here and told you that this was 7, and that the point up here associated with x equals 7 on the graph of f of x was 7, 2, then you would know that that means f of 7 is equal to 2. This might seem totally trivial, but it's an important thing to keep in mind. You'd be surprised how many problems can be made simpler just by remembering the connection between this and this. I'm going to draw for you another picture now. I'll put some space down here. Very similar to the first, but I'm going to mess up the function a little bit. Okay, so again here we'll say this is y equals f of x. Say this is 7, and that this height is still 2. But then I'm going to relocate this function value up here. So this point is now 7, 4. We're all familiar with the idea that if we have an open circle like this on the graph, that means the function value isn't determined by the height of that circle, it's determined by the filled in point above here. So in this case, f of 7 is not 2, it's equal to 4, because that's the y value of the point that's actually on the graph. But I want to start trying to understand what these holes mean in a little bit more detail. So imagine a little person, a little dude, walking along the graph. Near x equals 7. So here's my little dude. And what he's going to do is he's going to start walking closer and closer and closer to x equals 7, right? His x value is over here. We can track it. And he's going to approach x equals 7. As my dude x value gets closer and closer to 7, their y value gets closer and closer to 2, right? Because this dude is stuck along this graph. So as we bring him closer and closer and closer and closer, to having x value 7, the y values stay along this graph, getting closer and closer and closer to 2. The calculus notation for this statement, this boxed statement means, and it's just a bit of notation, that the limit as x approaches 7 from the left of f of x is equal to 2. And I want to highlight a little part here. Oh, I didn't write it in. It's closer and closer to 7 from the left the from the left portion, the fact that we're approaching from that side, is what this little minus sign here means. We put the minus sign above and to the right, like a superscript, almost like a power. But it's not a power. It's just the indication that my little dude is coming in from the left. So this is how we define a limit intuitively. If, as we get closer and closer and closer from the left, the y value along the graph of f of x gets closer and closer and closer to 2, we write that in calculus notation like this: lim x to 7 minus, the minus meaning from the left, of f of x equals 2. And similarly, as my dude's x value gets closer and closer to 7 from the right, their y value, well, let's see, if I was coming in from this way, so I'm on this graph, my feet are stuck to the graph, but I'm bringing my x value closer and closer and closer to 7. Again, my y value is getting closer and closer and closer to 2 because I'm stuck to the graph and because that graph comes in towards this little hole. So again here, the y value is getting closer and closer to 2. And just like the block of language up there has a mathematical notation, all of this block means that the limit as x approaches 7 from the right, and that's the plus, of f of x is equal to 2 as well. And here I'm going to do that highlighting thing again. So this plus indicates that we're coming in from the right. Okay. So these pictures take a second to digest. Today we are mostly going to look at examples of this sort. I'm going to show you all sorts of ways this can go nicely, and all sorts of ways this can go wrong. And then next week we're going to look very, very carefully at the explicit definition for a limit. But for now, I just want to give you a feel. Any questions about what this notation means or where any of these numbers are coming from? Like why a 7 here, why a 2 here, what does f of x here mean, any of that stuff that I can help clarify? Okay. Now we're ready to define if the limit as x approaches some number from the left of f of x is equal to the limit as x approaches some number from the right of f of x. we'll call this L. That is what it means to say that the overall limit lim x to a of f of x exists. And the value of the limit is equal to that shared value of the one-sided limits. So for example, in the picture or in the example from earlier, since the limit as x approached 7 from the left of f of x was equal to 2, and the limit as x approached 7 from the right of f of x was equal to 2, we say that the overall limit lim x to 7 without any plus or minus of f of x exists and is equal to 2. Now, who the hell is calling me? Oh, my office is calling me. I'm sorry. I need to take this. Hello? I'm good. This is Professor Faustic. I'm teaching right now. What can I do for you? I think you may have a wrong number. I don't teach that class, and I'm also in lecture right now, so I have to go. If you do need to get a hold of Professor Filesticker, you can send me an email or Canvas message, but you may want to check your phone number because that course code is not one which I teach. So I'm sorry, I have to go. I'm sorry. Okay. All right. So if we come back here to this picture, because when we approach from the left or from the right, our y values always go towards that same number, 2, we would say that the overall limit here does exist and is equal to 2, right? The overall limit being the limit as x approaches 7 of f of x. We would say that this does exist and is equal to 2 because the left and right limits match. It's worth noting here that the value of the function is not the value of the limit. So I'll add one last little comment about this picture. In the graph with the hole, the value of the function f of 7 is not equal to the value of the limit. Right? This fellow, f of 7, is equal to 4, and this fellow, the limit x to 7 f of x, was equal to 2. And if I gave you this picture back in pre-calculus, I bet you could have told me that this function isn't continuous. Even though we don't really have a rigorous definition of continuity, we have that intuitive definition that a continuous function is one whose graph you can draw without lifting your pen. It turns out that this distinction between the value of the function and the value of the limit is precisely how we define continuity in a way that doesn't involve any like bullshit, right? Like, about how we can lift our pen or not. If we want to be 100% rigorous in our mathematics, this is how we discuss continuity, by asking whether the value of the limit is the same as the value of the function. We are going to go in depth on continuity, but not this week. So there will be a few times in the lecture where I make a reference to continuity to kind of just get your brain ready and start thinking about it. But what I'd like to do next is just look at a bunch of different examples where you have a picture, a nice graph, and we want to discern some limits and function values from it. Before I do that, are there any questions on the statements and examples made here?
Can you go back to the example that you had written?
Which one?
The one on the second page?
So I think all I have so far are these guys, right? The one without the hole, the one with the hole.
Mm-hmm.
Discussion here. So we have our definition. This is the finishing of that discussion with a graph with the hole, and then our definition. And then another reference to that example. Is this the one you were wanting to talk about?
Yes.
Okay. Yeah, I'll hold here for a minute. We can make sure our notes are nice and pretty. All right. So let's take a look at some more pictures. I have here again some function, I'll call it f of x. We'll say that this is out at x equals 4, and this y value is 3, and this y value up here we'll call 5. Why not? Okay. So from this graph, I would like to discern a few different things. The limit as x approaches 4 from the left of f of x, called the left-hand limit. The limit as x approaches 4 from the right of f of x. The value of the function at x equals 4, and, if possible, the overall limit as x approaches 4 of f of x. So let's take a look. Imagine you're a tiny little guy walking along this graph, sneaking up on x equals 4 from the left. What are your y values getting closer and closer to?
Three.
Yeah, very good. Both in the chat and who is that down here? I'm sorry, I can't see the name. But yeah, both of you are correct. Jacob and why can't I see that name? Yeah, both correct. That's 3, right? Because if I'm glued to this graph, if my feet are glued to this graph, and I try to walk closer and closer and closer to x equals 4, my y values are going to get closer and closer and closer to this y value, which is 3. On the other hand, if my feet are glued to the graph over here, somewhere to the right of 4, and I allow myself to walk closer and closer and closer to x equals 4, what are my y values going to approach?
5.
Yeah, excellent. Thank you, Julio. So the left limit is 3 and the right limit is 5. what is f of 4 itself? What's the value of the function at 4?
3.
3. And what about the overall limit? What can I say about the limit without a plus or a minus here? Oh, I'm sorry, I need a little plus here.
It does not exist.
Very good. This one does not exist. And when you encounter these in the homework in WebAssign, they'll want you to type DNE. All right, this fellow does not exist because the limit from the left is different from the limit from the right. And I just want to say, if you were writing these down as I wrote them down, I forgot to write this plus at first. Make sure you go back and write that plus there. So the overall limit only exists if both the left and right limit exist and have the same value. So if these limits have different values, then the overall limit does not exist. And we'll see that there's a bunch of different ways for this to fail. Any questions on this example? And again, just to get us thinking, this graph clearly not continuous, right? I have to lift my pen right here. And that coincides with the fact that these one-sided limits are different. So once we have a nice rigorous way to talk about these one-sided limits, we'll have a rigorous way to talk about continuity. We're getting very close to that. Let's look at another example. Okay, so let me call this height 1. We'll call this shared height up here 4. And we will say that this guy over here does something like this. And we'll call this -1. All right, so this graph I'll call y equals g of x. And I'd like to, oh yeah, I'm sorry, over here, this is, we'll call this positive. I want to play around with a few different things. So again, I'd like to calculate the limit as x goes to -1 from the left of g of x. The limit as x goes to -1 from the right of g of x, and g of -1, and if possible, the overall limit there. And I'd also like to do the same thing on the right side. I'd like to calculate, sorry, at +1. I'd like to calculate the limit as x goes to +1 from the left of g of x. The limit as x goes to +1 from the right of g of x. G of 1 itself, and if possible, the overall limit as x approaches 1 of g of x. So let's start all the way over here in the top left. If my feet are glued to the graph of g of x and I am to the left of -1, so we're looking at this guy. So I'm stuck, my feet glued somewhere over here, and I want to walk closer and closer to having my x values be -1. What are my y values approaching?
-1.
Yeah, in fact, they're always -1 there. It looks like it's constant. Okay, what is about as I come in towards -1 from the right? So I'm coming in over here.
That would be 4, sir.
Good, beautiful. Okay. Maybe someone I haven't heard from yet today. Can anybody tell me g of -1? Beautiful. Yeah, excellent. Excellent. Both the responses in chat are perfect. g of -1 does not exist. -1 is not in the domain because there is no filled in hole anywhere here. There is no point on the graph of g of x associated with the input -1. So in this case, it's the function value that doesn't exist. That's kind of neat. What about the overall limit? The limit as x approaches -1 of g of x without a plus or a minus. Good, yeah, exactly. That one similarly does not exist. We can write equals dne if you want. That's never been, I always have a little bit of a headache when I see that saying it's equal to dne. But this is how WebAssign asks you to input the answers, so I'll do it like that. Okay, let's change our attention to +1. As I sneak up on +1 from the left, what are my y values approaching? Good, we're getting closer and closer to 4, right? As we sneak up like this. As I sneak up on +1 from the right, coming in like this. Good. In this case, what is g of 1 itself? Yeah, this is 4. And the overall limit?
Does not exist.
Good, yeah, this one does not exist. So in both of these, the overall limit didn't exist because the left limit and right limit are different. Left limit and right limit are different. In the case over here, g of -1 itself didn't exist as well. Over here, g of 1 did exist. So the kind of take-home message I want to drive in with these examples is that it's possible for all of these to be different. It's possible for the left limit to be different from the right limit. It's possible for the function value to be different from either of those. And it's possible for the overall limit to fail to exist if the left and right limits are not equal to each other. One more example like this, and then we're going to move to something a little more challenging. Okay, so maybe we do something like this. We'll call this, I don't know, 3, 2, and we'll call this f of x again. All right, so here, the limit as x approaches 3 from the left of f of x would be what? As I sneak up on 3 from the left, what are my y values getting closer and closer to?
2.
2, yeah, good. And as I sneak up on 3 from the right,
Also 2.
good, yeah, again, this is 2. So collectively, these tell me that the overall limit here does exist and is equal to that shared value of 2. What about f of 3 itself?
Yeah, it's not defined.
Yeah, this does not exist or is not defined. Okay, so it's possible for the overall limit to exist even if the function isn't defined at that point. All that's necessary for the limit to exist is that the left and right limits both exist on their own and agree with each other, are matched. Even if the function itself is undefined there, the limit might be defined there. And this is the connection to open intervals that I wanted to talk about. The left limit is determined by what happens on an open interval with right endpoint 3. Yeah, the fact that this function has limit 2, left limit 2, is because if you examine the behavior of the function on the open interval whose right endpoint is 3, you'll see that the function is tending towards 2 along that interval. And similarly, if you look at the open interval whose left endpoint is 3 and examine the behavior of that function there, it's tending towards 2. I do not care, for the purposes of the limit, I do not care what happens at x equals 3. I care about what happens nearby, right? I'm interested in the pattern. As we get closer and closer to 3, what's the pattern? I don't give a shit what the function actually does at 3. I could redefine the function at 3 to have a filled in circle down here or a filled in circle somewhere way up here, and that would not change anything about these limits, totally separate from the value of the function. At this point, the question I feel is fairly natural is, do these one-sided limits always exist? Is it possible for the one-sided limits themselves to have problems? If the one-sided limits aren't equal to each other, then the overall limit doesn't exist. We've seen lots of that. But is it possible for a one-sided limit itself to run into trouble? And before I talk about that, I want to talk a little bit about sine and cosine. So I'll hold here for a second in case anybody's still writing. But next we're going to look at some waves. All right, time to get wavy. This is an honors class, so I expect that you guys are really comfortable with the trig basics, but I think it never hurts to just take a quick look, because I'm going to do something weird with these. So graphs of sine and cosine. Here I'm going to graph for you sine x, and then below I'll graph for you cosine x. And especially if the graphing of these functions was something that was challenging for you in trigonometry, I want to make sure you get these into your notes nice and clear and follow the procedure I used to graph them. So first I drew the interval out 0 to 2 pi, and then I chopped it up into quarter periods, right? The full period for sine and cosine is both 2 pi, half period is pi, and a quarter period is pi over 2. So these are sort of the easy points to remember from the unit circle, and this is a little cheat code for drawing these graphs. Come in and fill in the easy points. Sine of 0 is 0, sine of pi over 2 is 1, sine of pi is 0, sine of 3 pi over 2 is -1, sine of 2 pi is 0 again. And then you know that the graph turns around up here, crosses here, turns around up here, crosses here, and then you just connect these little bits, and you get a very nice graph of the sine wave. All right, this is y equals sine of x, and he continues on and on and on like this forever, right? Just repeating this behavior every 2 pi. The graph of cosine x is very similar. Again, I'll chop up into half periods and quarter periods. Cosine starts all the way up at his max of 1, is 0 at pi over 2, comes through -1 at pi, is 0 at 3 pi over 2, and comes back to 1 at 2 pi. So he will look like this. big fat points there. Okay, this is y equals cos x. And of course, he continues on and on like this forever in both directions. Repeating. Sine and cosine are two super duper important examples. We'll refer back to them often. And these are both continuous functions, right? They're nice, continuous everywhere, nice and smooth. They're beautiful examples of functions that do all the things we want a function to do. What happens if I graph sine of 2x or sine of 3x or sine of 4x or sine of 5x if I start putting numbers in front of the x inside here? Does anybody
You
know?
will change the frequency.
Yeah, exactly. The frequency changes, right? The frequency goes up. Sometimes that's called angular velocity, or the frequency is related to the frequency. So I'm going to flip back to Desmos. Just pop open a new blank graph. We're just going to compare a few of these. Altogether, it's a mess, but here's regular sine x looking just like we drew it. Here's sine of 2x, and if you compare sine of 2x to sine of x, you see it's got a period that is half as long, or a frequency that is twice as high. Sine of 3x, compare that to sine of x, he's even more squished together, right? He's oscillating even faster, he's higher frequency. Sine of 5x, higher frequency still. So as the thing inside sine of x grows more rapidly, right? 4x grows faster than 3x, grows faster than 2x. As the thing inside the sine of x grows faster, the sine wave oscillates more rapidly. So what do you think the sine of 1 over x looks like? Here's the graph y equals 1 over x. We should remember this. This is one of our basic graphs from pre-calculus. 1 over x near 0 gets really big, right? Near 0, 1 over x blows up to infinity. So this thing, as x gets closer and closer to 0, 1 over x gets bigger and bigger and bigger. It grows really, really, really fast. So what happens if I put that inside of the sine function? Well, we said if the inside of the sine function gets faster and faster growing, those oscillations get more and more and more rapid. Here is what happens. As the inside, the 1 over x part gets faster and faster growing, gets bigger and bigger, the oscillations get more and more and more rapid. This can be a little bit hard to even see. In fact, this graph becomes dense in the plane. It starts to look like it's all just red. But what's really going on there is just faster and faster and faster and faster and faster oscillations. This is another way that a limit can fail to exist. Because I cannot say that as x gets closer and closer to 0, these y values are getting closer and closer to any particular number. They're jumping back and forth insanely fast. So very rapid oscillations can make a limit fail to exist. For example, y equals the sine of 1 over x near 0. Now, I'll do my best to draw this. I turned to Desmos there because these are really hard to draw. He comes in looking somewhat reasonable. So let's see, how can I do this nicely? These aren't nice numbers, but we'll do my best here. So he comes in here looking fairly reasonable. But then he starts to oscillate so fast that this all just becomes a blur. So if I tried to look at the limit as x goes to 0 from the right of sine 1 over x, this limit does not exist, because I can't say that these y values are getting closer and closer to anything. They're bouncing back and forth so fast that there's no way to say as you get closer and closer to 0, the y value gets closer and closer to anything. Any guess that you would have for this limit, I can show you a point whose x value is very nearby, but whose y value is not nearby. So this sort of rapid oscillation can ruin the existence of a limit. Does that make sense? The idea that you can't really get closer and closer to any y value as you bring x closer and closer to 0 here, because it just bounces back and forth faster and faster and faster. It is possible that you have a rapid oscillation like this on one side, but then reasonable behavior over here, or vice versa. So I'm going to give one more example where we're deducing limits from graphs like this, and this time it's going to have all the nasties. All right. So let's say I have some function coming like this, and then it starts to oscillate. But those oscillations start stacking up in a way that is incompatible with decent function behavior, just a really pathological function. But then on the other side, it comes in here and plays pretty nice. Maybe this y value here, we'll say is 2. And then over here, we'll have something like this. We drift off on that side. So again, I'll call this function y equals f of x. We call this x value right here 5, and we'll call this x value right here -1. Let's see what we can say about the following limits. Limit as x approaches 5 from the left. The limit as x approaches 5 from the right. The overall limit as x approaches 5. The limit as x approaches 0 from the left. The limit as x approaches 0 from the right. The overall limit at x equals 0. And then we'll also look at the limit as x approaches -1 from the left. Limit as x approaches -1 from the right. The limit as x approaches -1 overall. And finally, f of -1 itself. Okay. So let's start at the top left again. As x approaches 5 from the left, as I walk along this graph, coming closer and closer to 5 from the left-hand side, I start to enter this wild oscillation. So what can I say about this limit?
It doesn't exist.
Very good, Julio. Perfect. What about as I come in from the right? So if my feet are glued to the graph over here and I start walking my way in towards 5 from the right, am I approaching any particular y value?
2.
Yeah, I heard it. Haley, that's 2. Perfect. Right? There's no problem coming in here from the right. And I don't care about the crazy bullshit that's going on at 5. I just care about the pattern as we come in closer and closer to 5. And there's nothing weird going on in this little part of the graph just to the right of 5. We are getting closer and closer to 2. What can I say about the overall limit at 5? Good, this one does not exist. Because remember, for the overall limit to exist, both of the one-sided limits have to be equal to each other. Well, if one of those doesn't exist, then it certainly can't be equal to 2, right? So the overall limit at 5 does not exist here. And this is kind of a weird way for that to happen, but it can occur. Let's jump to 0 now. As I approach 0 from the left, what is my y value getting closer and closer to? Good, 0. Right? If I'm glued to the graph and sneaking up on 0 from the left, there's nothing weird here. There's no hole, no special feature here. It just looks like a normal graph and it crosses through the origin. So as I sneak up on 0 from the left, my y values are approaching 0. What about from the right? Good, Kieran. Yeah, this is also 0. Right? As I come in this way, it looks like we're getting closer and closer to 0. And the overall limit is therefore 0. While we're here, it's also true that f of 0 is 0. This is what it looks like for a normal continuous function, right? Nothing strange at all. The left and right limits are equal to each other, so the overall limit exists. And all 3 of those are the same as the function value there. This is continuity, right? For a function to be continuous, we need all of these things to exist and match each other. And that's what we're used to seeing. That's the normal behavior. All right, it's a little hard for me to get everything in the picture here. I think that does it. As we approach -1 from the left, what's happening? Yeah, we're going to 2. And as we approach -1 from the right, coming down like this. Oh, I didn't mark it, did I? Let's call this -1. Yeah, -1. Okay, beautiful. The overall limit here wouldn't exist because these are different, right? Because the left and right limits don't match. What is f of -1 itself? 0. Good. So again, the function value can be totally different than either the left or the right limit. All of these nasty things can happen. And there's plenty of functions out there that do stuff like this, right? It would take some time, but I could find you an algebra formula for a function that does this. Okay. The last topic I need to introduce today is infinite limits. And we got a little preview of that when we looked at the graph of 1 over x. So let's use that for our first example. Actually, let me give you a really general example for our first guy, and then we'll look at some specific ones. So I'm going to draw here a function that maybe looks like something you saw in pre-calculus when you studied rational functions. Those are ratios of polynomials, remember? And let's have this, yeah, we'll have this go up on both sides, which means we need to cross somewhere here. Okay. So imagine I have a function doing something like this. We're all familiar with these dotted lines representing asymptotes, right? So this goes up and up and up forever like that. This goes up and up and up forever like this. Not quite straight up, but real close. This goes down and down and down forever like this. Not quite straight down, but close. I'll call this x value right here A. and this x value right here, b, then we would say the limit as x goes to a from the left, I'll call this function f of x. The limit as x goes to a from the left of f of x, we would call that plus infinity or just infinity. I'll write the plus infinity here to make a distinction. And if you want to sound fancy, the name for this symbol is a lemniscate, Lemniscate, lemniscate. But everybody just calls it the infinity symbol. We say that that's plus infinity because if I'm strapped to this graph and I'm trying to walk closer and closer to A, then my y values are going to explode. They're going to go through the roof. As I go closer and closer to A, my y values just get bigger and bigger and bigger and bigger and bigger. If I were to approach A from the other side, something similar happens, only now, instead of my y values getting bigger and bigger and bigger in the positive direction, they're falling through the floor. They're getting bigger and bigger and bigger in the negative direction. So we would call this negative infinity. There are different number systems out there that do incorporate infinities. The one that we use is called the extended real numbers. And in that universe, infinity and negative infinity are different things. There's one way you can think about the real number line as wrapping around a circle and meeting at the end where plus infinity and minus infinity are the same. That's not the system we use. We think of this as a line, and we think of plus infinity as being all the way to one side and minus infinity as being all the way to the other. So here I would say plus infinity and minus infinity are different. Therefore, what do you think is true about the overall limit? The limit as x approaches a of f of x in this picture.
Does not exist.
Perfect. But it's not always true that infinite limits lead to an overall limit that doesn't exist. So let's look at b. As x approaches b from the left here, f of x is going to plus infinity. And we don't have to write the plus. It's just, sometimes it's nice as a contrast. Because again, if I'm walking along this graph, then my y values are just going to go through the roof. And if I walk along the graph getting closer and closer to b from the right, again, my y values are going up to positive infinity. So in this case, the overall limit does exist, it just happens to be infinity. And if both sides pointed down, then we would say that the overall limit is negative. Is this making sense?
Yeah.
Okay. So Kieran, I'd like to hear a little bit about what's on your mind. What feels odd here? That's okay. So I want to encourage discussion. One of the really nice things, no, don't worry. One of the really nice things about this small class is that there is genuinely room for all of us to talk and be heard and share ideas. And that's the best way to grow as mathematicians. Mathematicians, we sit around, we drink coffee, and we tell each other they're wrong all day. And most of the time, we're all wrong. So whatever it is we're thinking, it's nice to share. At A here, if we sneak up from the left, my y values, they just get bigger and bigger and bigger without bound. So I can't say there's any finite number that my y values approach as I get closer to A from the left. Any finite number I will eventually blow past, right? Just get a little closer to A, you go up a lot further. So the only thing that makes sense to call this limit is positive infinity, because as I get closer and closer to A from the left, my y values are exploding, just getting huge. And you can kind of in your mind replace plus infinity with really, really huge positive number. Oh, no, you're good. it's very possible to mishear things. And I'll try to pause. If you ever need a second to pause and make sure everything in your notes is perfect, just let me know. It's a good idea to pause, especially in the online setting like this. So make sure we've got all the little minus signs and little plus signs and that we're comfy with each one of these being positive, negative, whatever they are. Because on the left side, we're going up to plus infinity, and on the right side, we're going down to minus infinity, and I consider those as different numbers, I'd say that the overall limit at A doesn't exist. But at B, from the left, we're going up to positive infinity, and from the right, we're going up to positive infinity. So here, the overall limit, I'm comfortable saying does exist because the left and right limits match each other. Even though they're both infinity, I'm okay with that. We can work with infinity. So some specific examples here. Let's calculate the limit as x goes to 0 plus of the natural log of x. A lot of the homework problems, not a lot, but some of the homework problems this week are like this, where rather than giving you the picture, I just say find this limit. On those problems, it's expected that you know the graph. So this is a good example of a problem where even though I'm not giving you the graph and you don't have algebra tools to attack this, you can still figure out this limit. It's just your first step needs to be cooking up the graph. Now I know pre-calculus at Santa Fe is a little bit weak, so it's very possible to get to this class without knowing the graph of the natural log. I'm going to draw it here, and if it's not something that you have committed to memory very clearly, please commit it to memory now. The natural log function has a vertical asymptote at x equals 0, which it approaches from the right. It goes through 0, 1, 1, 0. It goes through e, 1, and it continues to grow off to the right, albeit very slowly. This is the graph of the natural log function. It might look like it has a horizontal asymptote on this side, but it doesn't. It continues to grow without bound. It's just that that growth is incredibly slow. So now that we have this graph, what is the limit as x approaches 0 from the right of the natural log of x?
Be negative infinity.
Beautiful. This is negative infinity. Can I talk about the limit as x approaches 0 from the left of the natural log of x?
There's no function there.
Right. So imagine again what you would do if you wanted to estimate this limit. You would have to plug numbers into this function that are very, very close to 0, but are to the left of 0. So like negative 0.1, negative 0.01. None of those exist. The domain of the natural log function is just the open interval from 0 to infinity. There ain't nothing over here. All this stuff is empty. There is no graph over there. So this one does not exist. But this time it's because of the domain. And I think with that example, we've seen all the different kinds of pathology that you're expected to handle in a regular Calc 1 class. Now, where am I at time? We are exactly at the end of class, but I want to drop one more little thing on you to think about. Because this is an honors class, I think it's fun to give you guys some nifty examples from a little bit higher up in the world of mathematics. So I'll give a second to get everything nice and clear from this, make sure your notes are perfect and beautiful. And then I'll ask you to hang around just for a few extra minutes at the end so I can show you something called the Dirichlet function. Okay, dear Schley. Piecewise functions are something you should have seen in pre-calc. We will talk more about piecewise functions soon, but Dirichlet, and I pronounce it Dirichlet, not Dirichlet. The Germans call him Dirichlet. The French call him Dirichlet. The Dirichlet function is defined piecewise. And if you want to see a little bit more work with piecewise functions, you can watch the video from my regular Calc 1 class. Yeah, I'm trying to fix the camera now. I know, I'm sorry. Which is on the playlist in my YouTube channel. But the Dirichlet function is defined piecewise as follows. D of x is equal to 1 if x is a rational number. And it's equal to 0 if x is irrational. So the graph of this function is mighty strange. If x is rational, like 1, 2, 3, 4, or 0, then the output from the Dirichlet function is 1. This is what's called an indicator function or a characteristic function, because it blinks up to 1 if your variable is from a certain set, and otherwise it's equal to 0. So -1, that's a rational number. -2 is a rational number. You get the idea. 1/2 is a rational number. So at 1/2, this function is equal to 1. But right in here, at about 1.4 is the square root of 2. That's an irrational number. And right over here at 3.1, that's pi. Pi is irrational. So d of root 2 is 0. D of pi is 0. E, which is about 2.7, E is irrational. So this function has a point up here along the line y equals 1 at every rational number. That's every whole number and every fraction made up of whole numbers. And there's infinitely many of those. They're all over the place. But believe it or not, there's actually a shitload more irrationals, way, way, way more irrational numbers than there are rational numbers. So even though we only know a few of them off the top of our head, like root 2, root 3, pi, e, and so on, there's actually a way bigger infinity of irrationals than there are of rationals. They're all down here at 0 because the Dirichlet function outputs 0 if you feed it any irrational number. So this function is interesting. In fact, down here, there's so many more irrationals that the line at y equals 0 is basically solid. And up here, we have what is essentially a very faint sprinkling of dust along the line y equals 1. This function is discontinuous everywhere. At every real number x, d of x is discontinuous. So there is no real number a such that the limit as x approaches a of d of x exists. Imagine you wanted to say the limit as x goes to 0 of d of x exists. Then you'd have to say that as you walk closer and closer and closer to x equals 0, the y values get closer and closer and closer to something. But if you're close to 0, there's still infinitely many irrationals down here and infinitely many rationals up here between you and 0. This function is going to jump back and forth infinitely many times between any positive number and 0. And the same is true at every other number a. Pick any number a and try to take the limit there. This function will jump back and forth infinitely many times between your number and a. So the limit does not exist for any number. There's no value of a for which the limit of d of x as x approaches a exists. But if I modify it, I'll call it e of x, so that this function is equal to x if x is rational, and 0 if x is irrational. What I'd like you to do is find the unique, there's only one of them, the unique number a, such that the limit as x approaches a of e of x exists. And then find the limit. So if you want a hint, I did show this to my non-honors class, and I gave them a strong hint on this. You can look in my YouTube playlist for the non-honors lecture from today and see what that hint was, but I'd encourage you to play around with this a little bit without doing that. Use the exact same thinking that we used here to draw the graph of d of x to try and draw the graph of e of x. It'll look something like this. You'll have a faint sprinkling of dust along some curve, and then you'll have a much heavier sprinkling of dust along the line y equals 0. The graph is going to look very strange in the same way that this graph looks strange. But you will notice that there's one point where all of these sprinklings of dust coalesce, where if you get closer and closer and closer to some input, the outputs really do get closer and closer together rather than jumping back and forth infinitely often. This is kind of like the sine 1 over x thing in that it's got all this wild oscillation. But let me show you something cool here. If I multiply the sine of 1 over x by x itself, you still have wild oscillations, right? Look how cool this graph looks. Still have wild oscillations. But now, even though you're oscillating wildly, the oscillations are getting tighter. So as you come in towards 0, you would have a limit. It's going to take us some work. We're going to need some theorems to prove that the limit of this function exists. But the graph should be enough to convince you that it does, at least from the picture. The limit as x approaches 0 of this function from the picture is pretty easily seen to be 0. See if you can't come up with a picture for this modified Dirichlet function. Figure out the place A where the limit exists and the value of that limit. And this would be a fun introduction to this sort of things. Now, I'd like you to focus on the homework first. The homework for this week is not terribly tough. It's not terribly long. Most of it comes from graphs. And if there are any problems where the graph isn't given explicitly, then the intent is for you to remember that graph from your pre-calculus class, draw it, and then come up with the limit. Please don't cheat yourself on this by Googling or using graphing utilities to excess. If there is a function where you cannot think of the graph at all, look through your pre-calculus notes. Try to look back and come up with it on your own. That's what a mathematician does, right? Because when you're working on a research question, there is no answer out there in Google or Desmos. You have to rely on your own mind. So do your best to do that. And then if you get absolutely stuck on something, then it's okay to use Desmos or Wolfram. But work on the homework first. Put a real genuine effort into getting that homework done before next Monday. And if you get stuck on anything, don't hesitate to ask for help. I would much rather you ask me for help than Google or read something from Quora. If you're looking for an outside help source, I'll tell you something else. I actually moderate the subreddit r/cheat@math-homework. So if you're looking for a place where you can get reasonable answers, this is not a bad one. The answers here will be much better than what you find on Quora, but I would rather you work on this stuff yourself. If you're in trouble, send me a Canvas message or something like that. That's your best approach. Remember, I need your student teaching sections and I need your honors project topics no later than a week from today. And because the student teaching is first come, first serve, you want to look over those topics and make your decision as soon as you can so you don't run into trouble. That's all I have for you guys today. I thank you so much for being patient at the end of class. I know we went over time a little bit. Are there any questions for me before we sign out? Alrighty then. I do have an office hour today. The office hour starts right now at 1 o'clock. So I'm going to be moving over there. Or not right now, starts in 30 minutes, sorry, at 1 o'clock. So again, thank you guys for being patient, really been lovely. I'm excited to get to know you all better. Don't forget to send me your student teaching and honors project ideas and get that homework ground out. Next week, we're going to look at the explicit definition of a limit, and we're going to talk about limit laws. Now, limit laws, I think, might have been one of the topics that you could choose for your student teaching. So again, if you want to get an easier topic, remember to pick soon, because most of the easier topics are towards the start of the semester. That is it. I'm going to end the meeting here. The link to the YouTube video will be up soon. If you want to watch the non-honors class, that's also on my YouTube in a playlist for the MAC2311 section 002 SP21. All right, that's it. Take care, guys. I will see you on Monday.